And now let's go back to diodes. What you probably know are these ones. These are regular diodes. We call them rectifiers because they are actually used for what? They are used to convert the AC into DC. Smaller ones or bigger ones. As you can see, the body is either made of a black plastic, like these ones, or it may be a combination between black plastic and metal, because sometimes you may need to put them on heat sinks if they heat up a lot, okay? And these ones are made of what? Silicon. So let me see the plan for today. Number one, we're going through introduction to some physics and chemistry behind LEDs. This is what I wanted to actually start right now. Then I'm going to make a summary about LED classifications, how to properly bias an LED. Next, what happens to an LED when it is over-energized or overpowered, and how to calculate the limiting resistor dissipating power, PD. Let's start with the measurement. We put a meter on diode, we pick up one of them, and we measure. The diode has two terminals, as you know, anode and cathode. On the rectifiers, they always mark the cathode. If the body is black, they're going to have a kind of lighter ring, like this one is a kind of silver color. And you're going to see on the meter that you're going to see some indication there. The indication is not very relevant, but if you use the same meter all over again, you're going to become used to these numbers. Why the indication is not very relevant? Because the number may not be the same if you use another kind of multimeter. However, because I use this multimeter for a long time, that's the kind of number I'm going to see when the diode is made of silicon. So now I'm energizing the diode in such a way that it's conducting. This is why I can see some indication. If I put it opposite way, the diode won't conduct, so my meter is going to show me overload or infinite value, like an open circuit. So open circuit, because now the cathode is aligned on the red of the meter, and the anode is aligned to the black of the meter. In order for a diode to conduct, it has to be aligned with the anode to the red and the cathode to the black. This is a bigger diode. Let's suppose I don't know which of them is the anode, which of them is the cathode. It just happened I connected it in the conduction order. So the terminal on my left is the anode, the one on my right is the cathode. If I put it opposite way, like this, it won't conduct. Open circuit. But again, what do you notice? You notice that the body of both diodes is an opaque body. They don't emit any light. So let's go for some very quick description here. The most common materials they used for years to build semiconductors are germanium and silicon. The germanium has 32 electrons around the nucleus. The silicon has 14. I'm not going to go describing the atomic structure of the germanium and silicon and so on, don't want to bother you. But what's common for both, because they can be used as semiconductors, they have 4 electrons on the outermost orbit. So on the outermost shell, 4 electrons are found. So these ones can be used as semiconductors if they have 4 electrons on the outermost orbit. If it is less than 4 electrons, what is less than 4? 1, 2, or 3? We have metals. If they have more than 4 electrons, more than 4, meaning 5, 6, 7, and 8, They are insulators. So in order for the material to be a semiconductor, it has to have 4 electrons on the outermost orbit. Okay? So far, so good. Now, the thing about that is, when you measure a diode, a rectifier, you knew already something about VF, which is the forward voltage. So at what voltage the diode starts conducting? What is this about? Because for the germanium is around, let's say around 0.3, and for the silicon is around 0.7. So it's lower for germanium and it's higher for silicon. Why is this? Everything relies on the actual atomic structure of the material. This one has 32 electrons. So the electrons around the nucleus are organized on 4, you can call them levels or shells or orbits. So the nucleus is somewhere in the middle, and there are 1, 2, 3, 4 shells around. As here the silicon, so let's say there's the germanium, and there's the silicon, there's the nucleus, and you have 1, 2, 3 orbits. In other words, one of the 1, 2, 3, or 4 electrons on the outermost orbit is a bit easier to take away from germanium because this is farther from the nucleus. Then if you want to take away 1, 2, 3, one of these 4 electrons from the silicon because they are closer to the nucleus, so the force required is a bit bigger. This is why, to make the things a bit simpler, the forward voltage is 0.7 volts bigger because you need a bigger force to take them out than if you need for germanium. Okay? So everybody knows about the voltage you measure across a diode or across a transistor junction, if it is germanium made or silicon made. Now, the thing is, we're going to measure around with our LEDs. And we're going to notice something interesting. I have here a testing circuit. So I have 2 LEDs. And if I measure the voltage across this blue LED here, what you're going to notice, hey, is not 0.7 volts, it's 3.1 volt. Imagine. And if I remove this one from here, and I pick up another one. Let's say I pick up a red one. This one you can clearly see it's red. Okay. So let's connect it here instead of the blue one, and we take the same measurement. So the voltage is not the same. Okay, the voltage is not. Why the voltages are different? Interesting thing to know about. Okay, why the voltages are different? So the voltage is not the same as before because the material they are made of is not the same. Now again, that's a silicon-made diode, a rectifier. This is not silicon-made because the silicon does not emit light. If you want, I can draw something else for you here. That's the symbol for a diode. This is the casing of a diode. So here it shows the direction of the flow, if the conventional direction of the flow, from the anode to the cathode. That's the symbol for a rectifier. But if you see such a symbol over the diode, like this, 1 or 2 or 3 arrows going to the diode, that's a photo diode. exactly like the solar cells, everybody knows. So the silicon is capable to convert a fraction of the energy coming in a form of light into electricity, but is not capable to convert the opposite, the electricity, into light. This is why they had to find other materials. So unlike the standard materials they use to build semiconductors, germanium or silicon, let's say if they want to build a red LED, light emitting diode, they're going to use something made of gallium and arsenic. So it's going to be something like that. Don't worry, the arsenic is not only a powerful poison used in electronics, you can get LEDs. So you can find other combinations. This is why the voltages are different for different diodes, because the colors are different not because of this plastic casing. I can easily prove this to you by using another one which is transparent. So this is not a transparent light. The kind of light you are going to see is only if you energize this diode, so you place it into a testing circuit, and then you measure the voltage across, or you watch the color given by the diode. So if I'm picking up this one from here, and I connect it instead of the red diode, like this, this is a white diode. It's a white diode. But if I remove it from here and I connect this one, what color is? You can take a guess, but don't, because it's a waste of time. We won't know until we connect it here. So this was the blue one. And if I remove it from here and I connect another one, this one, you see, this is a green one. So it can be a different one depending on the actual material hidden underneath. If it doesn't show, it's because it's connected opposite way, as you may expect. See, that's a yellow one. Okay. So for the yellow one, if you are measuring the voltage across the diode, you're going to find another value. Okay. So the voltage depends on the material they use to build the diode. Okay. We can measure with a lot of accuracy the voltages. There's not a point. So now I'm going to make a very quick classification of the diodes in two categories: LEDs. They are the diodes used for lighting, like here in this bulb are diodes used for lighting, exactly like this one here. Okay. And LEDs for panel indicators. These are the ones we're focusing on for panel indicators, because the same kind of LEDs are used to build the 7-segment displays. Now for these ones, we're going to split them in a first classification in two categories. Let's say standard LEDs, and I'm going to say red, green, yellow, amber. I should have some right here. This is an amber LED. If I connect it over here, the amber LED is going to be like that. That's the amber LED. Okay? Very good. So these are standard LEDs. What is common for them? The voltage at which they start conducting is around 2 volts. Some of them, like the red, are 1.7 or around, and some others, like green and yellow, they may go up to 2.15. Okay? But we take the average, considering 2 volts is good enough. And then I'm going to say special colors, special LEDs, and I'm going to put here the most common, the blue and the white. What's characteristic for both of them is the forward voltage is between 3 volts up to 4.5, depending on the actual combination of materials they're made of and the manufacturer. Okay? So there is a big discrepancy between the standard ones around 2 volts and the other ones up to 4 volts. Okay? So that's the first classification we make. Let's go further now. Remember that the color of the LED is not necessarily given by the color of the enclosure. For this one is really obvious because they used the resin, the plastic it is built of, to emphasize the color of the LED. But for the newest generation, the most of them are transparent. They come in a transparent body. And then, in the moment you power them, you energize them, then you understand what is the actual color. And there are also some very special diodes. Let's say they have an arrangement where they have one diode like this, in parallel with another diode connected opposite way, and out of that assembly, they have 2 terminals. If you energize this one forward way, you have a red. If you energize this one opposite way, you have a green. Let's take a look. Let me just find it. It may be this one. I put it one way. It's a green. I take the same diode. I just shift it 180 degrees. I put it like that. It's the red. So how come is this possible? Because they have actually 2 diodes inside the same body against each other. Okay? 2 diodes against each other. See? And of course, there is another famous arrangement, the RGB, where you can have out of the body. So let's say this is the body of the diode, and in the bottom here you have 1, 2, 3, 4 wires. One of them is the common, and then it's going to be the red, the green, the blue. Okay? So this one is going to have 4 wires around. One is going to be the common, and the other ones are going to be the wires for the 3 diodes. See? But for the ones we are dealing with, the most common of them, they are just standard anode cathode. Good. Let's go further. We leave this one away. So remember, we talk about testers next time. We leave these ones away. And now, we are going to come back to our plan. Okay? For the experiment organized for one red 10 millimeter LED, we're going to study this diode to see how is this operating. So in various working conditions. Now, We talked a bit about the physics and the chemistry. We talked just a bit about the classifications, not much. Now we talk about how to properly bias an LED. So we're going to build our circuit. This is going to be the power supply, plus minus. And right here are the two connections of the power supply. What's on the right side of this dotted line is going to be the load. So as the load we have a resistor, our LED. So that's the symbol now you just discovered for the LED. It's a kind of symbol for a lightning going out, meaning it's emitting light. And in order to monitor what happens, we're going to insert an ammeter here. And exactly as I say here on the list, an ammeter on the range of 400 milliamps. As a general rule, for all the diodes, regardless if they are rectifiers or LEDs, they need a limiting resistor, because in the absence of that resistor, you burn the diode right away. Our limiting resistor R is going to be 50 ohms. So to make sure, because we're going to put the diode in very harsh conditions, this resistor here, which is 50 ohms approximately, it's a 5-watt resistor, because I don't want the resistor to heat up too much. This is the resistor we connect right here. We're going to pick up one red LED, let's say this one. What we're going to need, never use a breadboard for that, because if you overheat, you may damage the breadboard. Instead, we're going to use alligator wires. I just went to buy them today. The alligator wires, $3.80 approximately, all the 10 of them. Here is a white LED, I paid 70 cents for it. You were seeing it before. Another one, the yellow one, I paid 40 cents for each. And the 50 ohm resistor, I just paid a quarter. That's it, okay? So I didn't pay much for them. Now I'm going to pick up one wire from here. And let's see what we do. To make the experiment right, the first thing you do is you bring the voltage to 0. Connections are made with the power off. So now we pick up the two connections here and we follow the diagram. This is the red of my power supply. I bring it to one leg of the resistor, like that. The other leg of the resistor has to come to the anode of the diode. We're going to talk about that next time when we build the testing circuits. How do you identify the anode and the cathode properly on a diode, on an LED? Now we just make the connections. If you don't know how to identify, you're going to measure with the multimeter first. So we connect the diode to the resistor. You keep a distance from the resistor to any other component, including the insulation of the wire, because it may heat up. Next, the meter has to be put on amps, and I just said on 400 milliamps, okay? And then the two leads of the meter, we're going to place alligators on them as well. And now we close the circuit. We close the circuit to the other power supply lead, which is this one, like that. So no other parts around. and the power supply is at 0, you just check the knob is completely counterclockwise. Okay? And here is what we're going to do. Good. We have here 1, 2, 3, 4, 5, 6, 7 columns. On the first column, we're going to monitor the current passing through our LED, because this is the key for our brightness. In order to control what happens to the LED, we're going to find out that the LED itself, it preserves a constant voltage the most of the time. What's going to happen? The current is going to vary. So we take measurements. The brightness is not a measurement, it's just our subjective impression about the LED brightness. The color is also an impression, but the power supply voltage we can measure, the LED voltage we can measure, and the resistor voltage we can measure. The very simple relationships to use are: the power supply voltage is as you could see here in the bottom, the power supply voltage, if I give it a notation, this is the voltage of the power supply. This is the voltage what I measure across the voltage across the resistor. And this is the voltage I'm going to measure across the LED. So because they respect the Kirchhoff's law, the power supply voltage is going to be the sum of the voltages around in series. As the ammeter is almost 0 ohms, we assume that the voltage across the ammeter is 0. So voltage of the supply is the voltage across the LED plus the voltage across the resistor. Okay? At the end, we're going to be able to calculate the dissipated power when we have the measurements. So let's start to do it. We have the diagram here. And now we try to fill the table with measurements. The power supply goes on. The meter goes on. We want the meter to measure DC on the range of 400 milliamps. And with the other meter, we're going to measure voltages. Okay? So now, what we're focusing on, we just very gently turn the knob clockwise of the power supply until we get a current passing through the diode here, 5 milliamps. Just watch the multimeter. Okay? Very gently. You see it's going up. 1, 2, 3, 4. Very close. The very small amperages are not easy to get. So we oscillate around the value a couple of times until we get it. One more time. Something like that, okay? Approximately. So here we can see the light over the LED. I'm going to say here the light is dim, the color is red. Power supply voltage. So I measure across my power supply right here, approximately 2 volts. Voltage across the LED, 1.7. Guess what? The voltage across the resistor should be somewhere around 0.3 volts. 0.25 is right there. The measurements are, we can approximate the measurements. Very good. Now we go further. We do what? We continue turning the knob But now we get 20 milliamps. Can you see the light is brighter? This is the actual normal light for a 10 millimeter diode. Okay? So brightness, normal. The color is red, no changes. Voltage. The voltage across the diode, we measure it, 1.8. So the voltage goes just a bit higher. The power supply voltage, it should still be the same, 2.95. It's not the same because we modified it. And the voltage across the resistor, 1.07. 1.07. So far so good. Next value here is 50 milliamps. Be careful. I didn't tell you that yet. I'm telling you now. The second classification of the diodes is about their size. I'm going to write here 3 typical sizes for the diodes. The size is measured in the metric system, in millimeters. And it's going to be the diameter of the diode, 2 millimeter diameter, 3 millimeter diameter, 4 to 5 millimeter diameter, and 10 millimeter. Here I'm going to give you an indication, so guiding info. If you want a good light over a 2 millimeter diameter diode, or for both of them actually, it's going to be something between 5 to 8 milliamps. 4 to 5 millimeter diode is going to be anywhere between, let's say, 8 to 20 milliamps. And for the 10 millimeter diodes, anything from 8 to 30 milliamps. So don't overcome 20 milliamps for the 4-5 millimeter diode. Don't overcome 30 milliamps for the 10 millimeter diode. Now we have a 10 millimeter. And don't overcome 8, let's say maximum 10 milliamps for a 2-3 millimeter diode. You want to see these diodes to recognize them later. I have some here. These tiny things I'm taking out of the box is a 2 millimeter diode, 2 millimeter LED. When we're going to test them next time, you're going to see it on, okay? Next, if I'm going here in the box, that's a 3 millimeter diode. So compared to the 2 millimeter, you can see them both. 2 millimeter diode, 3 millimeter diode. Next, that's a 5 millimeter diode. So what am I talking about here? Is the diameter in the metric system, 2 millimeter, the body of the diode, 3 millimeter, 5 millimeter diode, and of course the one we are using right now, 10 millimeter diode, these ones. You see, bigger the body, bigger the amperage. That's the relationship, okay? Bigger the body, bigger the amperage. Excellent. So now we have an idea about that. Because that's exactly what is our experiment about. In the moment we overcome these amperages, like we play right now with the 10 millimeter diode, and the normal current, this is why I can leave it like that for days, it's going to work just fine. And the temperature, I can measure the temperature of the limiting resistor. It's exactly the room temperature. If I measure the room temperature anywhere, so it's 20 Celsius degrees in the room. This one is 23.8. So it's just a bit warm, okay? So it's a normal temperature. But we go further. We increase the current into the LED to 50 milliamps. And as soon as you do this, you have to take the measurements relatively quickly So now I'm going to talk less and I'm going to take the measurements quickly, because otherwise I can damage the diode. Okay. So now you take a look at the ammeter. I go to 50 milliamps. And as soon as I do, I take measurements. Power supply voltage, 4.8. The color is red. The diode is very bright. The voltage across the diode, 1.96. The voltage across the resistor, 2.66. I go further. Next value, 100. Let's see, around 100. I go quickly across the power supply, 7.7. The diode is still very bright. I go across the diode, 2.2 volt. I go across the resistor, 5.2 approximately. We go further, 150 milliamps. Quickly, because the diode, you see, you increase the current, we increase the current a lot, but the diode does not become any brighter now. Measure the power supply voltage, 11 volt. The voltage across the diode, 2.5. Voltage across the resistor, 8 volts. And if it is possible, I'm going to give it 250 milliamps. But you see, suddenly the diode becomes dimmer and it gives up. It did not support a 200 milliamps, it gave up. So I won't be able to fill this one because it became dimmer and dimmer. It gave up. I cannot take the measurements. So that's actually asking the question, what happens to the diode if you over-energize it? You see, the current is still passing through the diode. It's completely shorted right now, so it doesn't worth the effort to continue energizing it. If I take a measurement of the resistor, it's still not too hot because it's a 5-watt resistor. So the resistor is, if you take a look, 28 degrees, okay? But the diode gave up already. So this diode has to be disposed after that because it's useless. Now, how do we interpret the measurements? Because we took approximate measurements, we can take a look here. If it was 175 volts, 175 plus 0.25, it was 2 volts. So obviously, respecting the basic relationship here. Similarly here, approximately 3 volts, 1.80 something plus 1.1, 2.9, approximately the same. 4.8, here 2 volts, plus 2.66, 4.66, not far from 4.8, 7.7, 2.2 plus 5.2, so it's not far, because it's 7.4, and here 2.5 plus 8 is 10.5, not far from 11. So we can say with the approximate measurements we took, the relationship is respected. And now the resistor power dissipation, which is the current passing through the LED, we have a series circuit. We have a series circuit here. So the same current passing through the LED is going to pass through the resistor. So if we just multiply 50 ohm resistor by the milliamps, we have the power in milliwatt. So no big deal to convert it there in watt if we need to. So 50 times 5 is 250 milliwatt, so 0.25 watt. Here, 20 milliamps times the same resistor 50 is 1 watt. 50 is 2.5 watt. 100 times 50 is exactly 5,000, which is 5 watt. So you see, we did not overcome the maximum power of the resistor, but if we hold this for a longer time at higher amperage, the resistor is going to heat up. So that's the thing about the circuit where you connect a diode. Not only you have to provide a limiting resistor, and what the limiting resistor purpose is to maintain the maximum recommended amperage through the diode. Example, if I want to energize the 4 to 5 millimeter diode, the current is going to be anywhere between 8 to 20 milliamps. I would recommend, let's say, 10 milliamps. And if you connect here 5 volt for the power supply, and you know that the voltage across the LED, as the voltage went bigger and bigger from the power supply, the voltage was not exactly maintained identical through the LED. But let's say from the first to the last value, if we calculate the average, is somewhere around 2 volts. So the voltage across the LED remains around 2 volts. Where is the rest of the voltage dropping across that resistor? This is the one absorbing the difference in voltage between the power supply and the LED. This is why it's called the dissipating resistor or the limiting current resistor, because it limits the maximum amperage passing through the diode. Now, when we have 5 volt the power supply and 2 volt the LED, the voltage across the resistor becomes 3 volts. So, for the resistor here to be passed by 10 milliamps, what resistor should be there? The new resistor should be 3 volts, which is 3000 millivolts, divided by 10 milliamps, is approximately 300 ohms. So anything around 300 ohms is going to be good if you want the current to be maintained 10 milliamps. That's how you calculate the resistor, but there's something more, and this is where the dissipating power becomes important. What power should that resistor dissipate? Because you don't want the resistor to heat up too much. We have to multiply the amperage times the voltage, because another way to calculate the dissipated power is voltage times amperage. So remember, the power can be calculated as voltage squared over the resistor. It can be calculated as squared current times resistor, or it can be calculated as voltage times amperage. Okay? So this is the one we use right now. And in that situation, the voltage across the resistor is 3 volts. The current is 10 milliamps. So it's going to be 30 milliwatt. So any small resistor you can buy, like if I pick up one small resistor from here, this is a half watt resistor. Is absolutely sufficient for the job. Okay, you don't need that huge one, a 5 watt. You just need this one. That's how you calculate it. Okay, so that was the use of knowing all these things measured in a testing circuit for a diode. So far so good. So in order to build more performant testing circuits for our diodes, let's see you next time. Thank you very much for watching. Bye-bye.